Hello, everyone, and welcome to the fifth Agda problem-solving session of the HoTTEST Summer School. So in class, we discussed some more hits, and in particular, in lecture 4, we saw the recursive principle for hits, like the circle. And then last class, we saw the full eliminator, so the full dependent eliminator. And some of the exercises that we were supposed to do last time was to show that if we have these two models of the circle, one of which has one point in a loop and the other one of which has 2 points in two loops called east and west. Well, not loops, they're no longer loops, two meridians, east and west. Then those two circles were the same. And last time we constructed two functions, two from base and two from loop. One of which said that I guess in lecture 4, we constructed the functions to and from. If we look at what these functions are, 2 is a function from S1 to the 2-point circle, and from goes in the other direction. So we've shown that in this composite, to first and then from, if we just evaluate it on base, we get base. And if we apply this composite onto the loop, we get loop. And the question was, well, then can we show that to composed from, or from composed to is, I guess, how you'd read it, whether that function is homotopic to the identity function. Whoops, wrong file. And that's the very first exercise. So this was a question last time that was asked, and then I said we can't do it because we don't have the dependent eliminator. Well, now we do have the dependent eliminator. So we're constructing a dependent function from the circle to this equality type that's parameterized by points in the circle. So if we look at lecture 5 notes, then what we have is this dependent eliminator for the circle S1 elim. And the first thing that it takes is a type family given as a map from S1 to type. So because we want to construct a function from S1, and it's a dependent function, we're going to use the S1 eliminator. Then I should say what the motive is. And the motive is this. Then I need to construct 2 arguments. The first argument is from to base equals base. Well, if I look at my solutions 4 file from what we did last time, that proof was just reflexivity. But we gave it a name. Now, we'd hope that for the next case, we can just put 2 from loop, but it's not going to be that simple. What we're going to need to produce instead is a path over, which is a construct that was introduced last time in lecture. And so we're done modulo this whole. Now, here we look at what we did in lecture when we were considering the other composite. And we proved a certain lemma, which was a bit mysterious. And it was this round trip lemma. And what the round trip lemma says is that if we want to construct a path between Q and R, where Q and R are 2 different paths from GFA to A and from GFA to A prime. And if we want to construct a path between them that goes over GF of P, then it suffices to construct the following path. And so this looks a bit confusing. So let's see what this looks like. So we have basically f and g, their functions. Let's say x, y, x. And let's just look at the order. Well, we're going to be doing f first. And then g. So I think this is well worth doing because that lemma was like pretty mysterious in class, I think. as when it came up. Do other people have thoughts on this? Okay, I see a thumbs up. So then suppose that we have points A and A prime. Yeah, all of the dependent path lemmas are a bit mysterious. Yes, I agree. So we have 2 points in X, and we have P path connecting A and A prime. And then what we have is basically 2 paths, which are called in this notation. 1 second. Let me just fix a few things. Q and R. So Q is going to be a path from G of F of A to A. And R is going to be a path of G of F of A prime to A prime. And the question is, well, suppose that you want to consider a path P, or another way to write it would be an equality Q to R in the space dependent on an identification between 2 types. So an identification from this type to that type. And how do we identify this type to that type? Well, we can imagine that if we have sort of the path from A to A prime, we're going to apply the function G of F of lambda X using Agda notation, G of F of X is equivalent to X. So this gives for every point a type. And then the notation that we're using in Agda is we are putting a down arrow over P. So this is what we want to construct. But I'm going to claim that we can characterize it in a different way using path induction. And so let's see what that should be. So if we sort of imagine our space, I'm not sure if this is going to be helpful. And we have, I guess, A prime and G of F of A. And then we have a path here and a path here. Then the question is, what would it mean to produce a path between these that's dependent on a path here? And sort of the characterization that you'd think of is, well, let's say that we want basically it's to be an equality of okay. So the idea is this. If you consider sort of transporting, so now this is going to be a bit of a spoiler, transporting it over the path P. And then you're applying this transport to the path Q. Then you can show that that's actually going to equal, well, this is going to be So Q is some equality from A to G of f of A. And the result is going to be some equality from A prime to G of f of A prime. And so what equality is that going to be? Well, the idea is that you tack on paths here and here. This path would be app G app F. I think we want to write it separately. Yeah, it's written separately. Of P, and this path is P. Sorry, yeah, P. So a reasonable thing to write that's well typed, is that this is going to be the path which first does P inverse. That takes you from A prime to A. Then what it does is it does the path Q. And then what it does is it does the path app G app F of P. And this is just an equality that's this equality is well typed. That's the key. And so then I can try and prove it, and I prove it by path induction on P. And when P becomes reflexivity, this transport, it's just transport over reflexivity, so it's just definitionally Q, and then this is just definitionally reflexivity, and then this is definitionally reflexivity. And I guess we have refl dot Q, so we have to apply the left's identity law, but then we get Q equals Q. So we can prove this when P is reflexivity. And then by path induction, it gives us the statements. Well, we have a characterization of these dependent paths over as being transport of the left-hand side is equal to the right-hand side. So a good conjecture would be that it suffices to construct just this thing that we have here. And an equality between this and Q. Now I've chosen to write it in this direction because that's the direction that's it actually well, it's supposed to be transport this equals to R. Is that what the chat question is? Oh, okay, yeah. So I'm going to put an R here, and that's what I want. Okay, now ask the basic question because this exposition is finished. And can you unmute yourself as well? That would be good.
Hello?
Yep.
Okay. So I guess I'm just I'm not sure what a path over actually represents. In the general case, it's not a path. In this case, it's a path because we have the type family over which the path over is defined takes us to 2 points that happen to be in the same space, and so everything's are paths in the same sorry, not space, type, or maybe I do mean space. Same thing. And so we can draw paths between all those guys. But if in the general case, the type family, because it's a dependent function, could take the two endpoints of the path to different types, couldn't it? In which case, what is the path over? It's not a path with extra. Is it a path with extra stuff? Is it a completely new kind of entity in our theoretical framework? What is it?
So there's a special characterization that happens here, where basically if we're transporting in sort of a space like x equals x, then transport x by conjugation. And if instead of having x, you have gf, then you get this characterization. So that's why this reduces to this. But in general, what you should think of is that path over. So if you have basically some sigma type, so sigma x in A of B of X. This is your general sigma type, right? Where B is some function from A to type. Then what happens is, let's say you have an equality, A is equal to, and then I'll write inside A as a subscript to A prime. Then if we consider equalities between, let's say, A, B, and A prime, B prime in the sigma type. So I'll write it like this. Then we have a characterization that this equality type is equivalent to the sigma type of first equalities P from A to A prime. And then from transports in B. I think I want to write this as a subscript in B over P of little b is equivalent to B prime. And so what transport does is that in general, if you have basically a type family, so let's say this is A and this is B, then you have here a point B, and what it lives over is A. And if you have any path from A to A prime, then you get a transport, which gives you a point transport B P of B. And then you can imagine that there's sort of an implicit path living over here. In cubical, we can write down what that path is, but at the moment, just imagine that there's a hypothetical path connecting these two. And what transport does is it gives you this endpoint, right?
So,
but now you have some other point over A prime, and that's B prime. And so the characterization, and this is proven by a path induction, is that an equality between this pair and that pair consists of an equality P downstairs and an equality Q upstairs in the fiber in B of X.
You drew a singular B though, and B is actually a family, which could be different for A or A prime, right? Big B, I mean.
B is, this is, yes, a type family B of, this is sort of the sigma type. You should think of it as, you can think of this, I wrote the points B, but really this is, B is not a type. B is a type family. But you can write the type family as sort of conglomerating all of the fibers into a sigma type, except for the fact that I actually want to draw points in B.
Gotcha.
So this is how we represent a point of B of A, and this is how we represent points of B of A prime. We sort of draw this being over it, and that suggests that this is sort of split into fibers that live over the points downstairs.
Okay.
So because of this characterization, that an equality between pairs is this pair of equalities, well, let's say you provide this equality already, right? Then it's reasonable to define an equality between B and B prime, except now I'm going to write that this is an equality living over P. So I'm going to write B down arrow P and B prime. So this lives in B of A, and this lives in B of A prime. Does that make sense?
Uh-huh. But what this is like, it's sort of the second projection of a regular path in the sigma type of B.
Well, so the catch is going to be that we've a path in this as the second projection of in the sigma type. It's not definitionally going to be that. But with respect to this characterization, we've already provided this path. So it has to be something that extends over this path. So one way of defining this, and this is the way that the Hot book defines it, is to say that this is just definitionally equal to transport B is equivalence to B prime. And in the lecture, we proved that these two are equivalents. Or I'm not sure if we proved that they're equivalents, but you can see in lecture 5 notes, one of the first characterizations that we have is transport to path over. That's actually, this is an equivalence. That's this type right here is equivalent to transport in B over P, B1 equals B2, which was what I was explaining. So actually, this is the way that you should think about it, is what I suggest.
Gotcha. Why do we define a separate data type for path over then, if it's really just this concept that already exists based on more primitive things?
Because you can do sort of better path induction over these. You get to do some interesting path induction that you wouldn't hear. I mean, this is also a path. The answer is that when I did regular Agda, I used this as my version of path overs, and in cubical Agda, there's a completely different version of path overs that works much better than both of these types. So I don't know. The answer is if the ultimate version is the cubical version.
Okay.
But that sort of makes this lemma reasonable. Then we can sort of think about what this lemma is saying, and then if you think about it, then what you want, if you want to construct this, then what you're actually asking to construct is an equality between this and R, right? This lives in the same type as R. However, if we look at sort of the left-hand side of what we want to construct, it's a transport that looks like this. And the question is, can we characterize this transport? And what you can do is you can write down this expression, and this expression has the same type as this expression. And when P becomes reflexivity, sort of using the left identity law, you can show that these are equal. So by path induction, we can characterize this pesky transport as actually being a concatenation of these things. And therefore, if we have this piece of data, it suffices to construct one of these. And we can prove that by path induction. So like most of the content is the statement that this expression is well typed. So I spent quite a while looking at this. In lecture, this was not explained at all. So I think that this thing was very mysterious. Yeah, well, okay, symmetry, sure. Dan mentioned symmetry as another reason. So let's go back then, and let's look at what the type of this is. So we need to give G and F explicitly. We need to give the path P explicitly, and then we need to give this witness. So now if I go to solution 5, which is what I want to do, I require to construct this path over, but it's a path over of this form, so I can use that lemma. Path over round trip equivalence is the name of that lemma. Then I should give G and F. G is from, we can see here, F is 2. Then what path do I want to have? So I have path over, and then I have loop. And then I have these two paths. These two paths are actually reflexivity if I fully normalize it, but the point is that P is loop. So I want to put loop as the next argument. And then if I sort of fully normalize this, you can see that both of those things, the two from base things, they're just reflexivity. So now I'm going to let Agda deduce some arguments. this is going to produce question mark and question mark here, and I'm going to let it fill in the reflexivities from the unifier. And then I want to see what I need to produce here. And what I need to produce here is a proof that's refl dot app from app to loop equals loop. But I have a characterization of app from app to loop equals loop. So that's to from loop. And that's gets me most of the way, except I have a ruffled base. So now I'm just going to look at sort of the lecture 4 notes and look at what my path algebra lemmas are. And one of them is dot units L. And I concatenate it with that, and I get the equality that I want. So working with dependent eliminators is sometimes annoying, especially when you have these path overtypes. And then you needed to characterize a transport in order to get this. But the point is we upgraded these two equalities to being actually a proof that the composite of these two functions is homotopic to the identity as a function on all points in S1. Any questions about that? Okay. And then there's we can just prove that now they're equivalents. In lecture, we proved one of the characterizations. And now we have the other characterization. So if we just look at sort of what we have a isomorphism. Or we can call it an equivalence. So if I just copy this over, then I can construct an equivalence where the map from S1 to circle 2 is 2. This map is from. This map is also from. So this is sort of the bi-equivalence version. So both bi-equivalences are the same. And then if I look what I need here, I need 2 from is homotopic to the identity, where homotopic is pointwise equality. This is from 2, so this is 2 from. That's exactly what I want. And if I just look at the normalized version of that type, that's exactly that. And then the other version is going to be called from 2. And that was done in lecture. So that yields an equivalence between these two models of the circle. Now we're going to do that again with another map. We're going to define a map that reverses the orientation of the circle. And we sort of did define this already in the previous one. So this is going to be defined by the non-dependent eliminator. Then I need to say where base goes to base. Where does loop go? Loop goes to loop inverse. So this is the function that takes a circle and it reverses the loop. It sends the loop to loop inverse. So you can imagine sort of if we have our models of the circle, then are just one model in this case. This is base. And here is going to be another circle base. And then we have loop. And let's say that loop is sort of oriented in this direction. And then I have a map that sends base to base. And as you go around loop here, it's going to send you backwards around loop here. So that's the picture of this map. And what we want to show is it's an equivalence. And sort of what should the inverse of this map be? Itself, yeah. So I'm going to write is equivalence rev. Well, to prove is equivalence rev, I need to construct an is equiv structure, which is constructed how? I'll just refine. So I need to give an inverse. I'll just say that the inverse on both sides is rev. And then here I need to construct two homotopies. And I think that I'm probably going to want to prove some lemmas, but let's see if I can do it inline. It would be interesting if I could do it inline. Well, actually, both of these composites are the same. So you know what? I'll just write, since it's the same. Where rev is a proof that rev composed rev is homotopic to the identity. Are okay, I guess these parentheses are necessary because that type has now if we look at what a homotopy is, it's a dependent map, right? So we're going to use the dependent eliminator, S1 elim. And the motive that we're going to pass to the eliminator is that for all points x, we want to prove, let's see. Oh, that's my personal convention. The question is as to where you put where. I think that in the code bases that I've seen, it goes here. The reason is that I sort of like to have this indented at the minimal indentation level. And if I put it here, then it says that like sort of the other stuff should be indented as well, because this looks bad. And then you have to do an extra space of orientation. So let's just look at sort of, it's going to be rev of x is x. That's the motive. Then I need to prove that rev of base is base. But that's just showing that base is base. So refl base covers that case. And now I need to show something interesting. I need to show this path over. But once I have that path over, it'll give me what I want. So it now suffices to construct this path over, but how are we going to construct that path over? It's a path over in this function x equals x over loop refl. So we're just going to use basically the same lemma that we used last time. And now we need to say what the maps are. They're rev and rev. And then what is P? It's loop, because that's what it says here. And then I need to construct something, and then that will give me it. Now I'm going to get the unifier to tell me what that something is. And it's a path that refl dot app rev loop equals loop. Now, we can sort of characterize, so at this point, I'm going to do some equational reasoning. So I'm going to start with this expression here. And I guess this is some pretty intense indentation for an equational reasoning proof, but sure. And I'm just going to use the left identity law so that I don't have this thing floating around. And then I guess I'll just do app underscore dots. So this is the map that concatenates this to the right of something. And well, Oh, right, of course. I should put a QED. And then it's going to tell me what the next endpoint is. It's don't so something went wrong. Don't you need app for the dot unit for the unit L? Well, I have oh, sorry, exactly, you're right, you're right. It's the left unit law on something. So that's why it was weirding out. It won't let me fill that hole. Yeah, good. No app, just this. Because yeah, we're fine. Now the catch is that when you do app rev onto loop, that's an instance of the dependent eliminator. Sorry, the recursor. And we have propositional computation laws for those in lecture 4 notes. And that propositional computation law is S1 rec loop. Oh, the shortcut for goal have is CCC dots. So CCC comma, 1 second. CCC comma just, sorry, I'm pressing meta. CCC comma just gives you the goal, and CCC dot gives you the goal and type, except for the fact that something happened. I pressed a key combo that made letters uppercase in Emacs. CC, yes, CCC dot, it gives you the normalized type. It's not CCCC, it's CCC dots. And then if you want to normalize it, you append CU in front of it. Does that make sense? Good. Okay. Now here we're going to do something. And let's just put app of app rev onto the front of this. And then let's do something with app rev. And what we're going to do is we're going to do the thing that I just cleared my buffer for. And I need to get it again. It's S1 rec loop. And then I need to say what X and what P are. So it's loop and inverse of loop. And that should evaluate this eliminator, and it'll give me loop inverse. Sorry, this is base, of course. Now I have app rev onto not loop, and I don't have a computation law for that. But I have from last time, I guess if we look at the solutions, we used it somewhere. We had app exclamation point. That if you app onto not F, then you get not of the app. It's not called not. This is just terrible notation. You shouldn't call it a bang, you should call it an inverse. But I'm reading it as not because that's what it says. And so that brings the inversion out front. And now I'm going to apply inversion onto the next computation law, which is the same as we had before. And it's going to give me not loop. Now, is not the same as just the regular thing? Well, it's not double negation, it's double path inversion, and the answer is yes. So we're going to call this a lemma, not. And then we're going to say for every type and every path in that type, we have that knots of knots P is P. And how are we proving this?
Path induction.
Yep, path induction. So we do induction on P. Let's call it reflex. And then we want to prove reflex is a reflex. So refl of X. And so now we do knots on loop. And that gives us loop, which completes this proof. And the red stuff is there only because sometimes Agda has that. So I kill and restart Agda, and then that happens. Okay, now I proved in rev, and I need to give this twice here. And that proves that rev is an equivalence. So there we go. Okay, how am I doing for time? It's 15 minutes. So there are lemmas about equivalences between the circle and the torus, and I didn't do that in the last lecture, last tutorial session. But let's just actually work out what this helper lemma that we'll need for the next thing is, and we'll see why it's going to be reasonable. So let's say that you're doing a proof. I think that these backslashes are sacrilegious and you should just type lambdas. So the claim is, suppose that you have a proof that f of a equals g of a and f of a prime equals g of a prime. So it's basically the same situation as we had before, except now the g is on the other side. Then when we do this transport lemma, we're basically going to ask ourselves, well, what about transport inside of the type lambda x, f of x is g of x. And suppose we transport over some path P, and what P is it's some equivalence from A to A prime, sorry, subpath from A to A prime. And then we're going to have a path R. Well, Q, I guess, first. And Q is going to be some path from F of A to G of A. Then the results of this is that this has type. Well, what's the motive? It's f of x equals g of x at A prime. Yes, this is actually f is homotopic to g. So yeah, we can write this in a different way. And I actually like that. This does not make it clear that this is a function, though. But now that we saw the other way, I can rewrite it. So what's type does this have? Well, this now I should write out what the definition is. It's for actually, no, there's a difference. There's a difference. This is for all x, f of x equals g of x. Whereas the other type is lambda x, f of x is g of x. So this isn't actually, this is actually a for all type. So it actually doesn't work. You could write this as lambda x to f twiddles g of at x. That's another way to write it. But you no, you can't write it like that. It's a different type. This is a function, the other is a type. F twiddles g is a type. This is not a type. This is a function from exit types. So there's a difference. Well, where this lives is it's f of a prime is equivalent to g of a prime. And what's another term that we can write in that type? So thinking about it like this, we have here f of a to g of a. And here, I guess I don't need to write parentheses, f of a prime to g of a prime. And there are paths connecting these. The paths that connect these are app f p. And this path is app g of p. And so what is a term? Well, we actually don't have the path. We don't have the second path. We want some term whose type is of this second path, right? Because we don't have a path. We have a transported path. That's one way to get the path. What's another way to get the path? What's another way to write this?
Just composing those three the same way we did with round trip.
Yeah. So we want to do this one backwards first. So it's app f p inverse. Did I write a bang when I wrote that out? I wrote an inverse. Dotted with the path that we have here, which is q. Dotted with app g of p. Right, I read paths from right to left because you start here and then you do something else. Oh, sorry. Am I making a mistake? I am making a mistake. I actually should be writing it the other way around. Yeah, that's sorry, left right dyslexia. This you actually do the first path first. So I've been writing it the wrong way around. Thanks for the correction. So you did mean it the other way around last time as well. P inverse dot q dot app g app f p. And then instead of writing that again, I'll just copy it over. Yeah, paths are written this way. Okay, so we basically found something that's well typed, and now we're going to see how we can prove if you have a well typed expression and it's true for reflexivity, which it is, then you can prove it. So here, we've decided that the type should be you first do app f of p backwards. Then you do q, then you do app g of p. And so this is something that has the potential to equal r. Because they're in the same type. And so there are a bunch of implicits here. I'm not sure if all of those are implicits are necessary. But the point is that you have H, and H is going to be some path here, although we actually want to do path induction on P. That would be the thing on which it is good to do path induction on. Because, yeah. I mean, we can sort of do an experiment and see what would happen, but we're going to do path induction on P. By the way, these arguments aren't necessary. If you want to just write it, you write P equals that. So I think maybe the arguments were written so that you'd have all of the implicit ones. But if you just want one implicit argument, this is how you do it. And so we want to construct a path over REFL. But to construct a path over REFL, it just suffices to construct a path over. And we prove that in lecture 5 notes using this path to path over. And so this is going to construct a path over reflexivity. And then if we look at what the type of H is, the type of H got reduced. It used to be this complicated expression, but when sort of P became reflexivity, this part computed away and this part just became an identity law. So we have reflexivity is R, but we want to concatenate that with the left unit law. So what's my left unit law? It's unit L dots H. Except I want to have it on the other side, so I'm going to invert this. And that's a proof that Q equals R, and that's a path. So there we go, we've proven that lemma. So now I think this was the valuable part, because I think that in lecture, this was very mysterious as to how that was derived. And now we've derived a similar lemma, but we're not going to use it because we're running out of time. That let us actually, and we saw how we came up with the lemma, and then we saw how we proved it. And then I haven't talked about the torus at all. So let's just look at what the torus is. We're not going to do anything with it, but let's look at what the definition is. So the torus is actually a pretty interesting type. So torus has two loops, and then there's an equality between the concatenation. So it's called P and Q of the torus. Let's see what this looks like. So there's a point, which is called base T. Then there's P of T and Q of T, and I'll write them somewhat suggestively. Like this and like this. So let's give them a direction. And the statement is that surface is going to be an equality. Surf T has type, well, rather ST, just ST. Has type PT dot QT. Is QT dot PT. Yeah. So it's a commutator between them. Now, sort of, one other way to picture this is suppose that we had a square. And suppose that we had paths that were this was the path. Okay, one way that we can get the torus is like this. We make an identification of this side and we make an identification of this side. Then this point becomes identified with this point. This loop becomes identified with this loop, and this one becomes identified with this one. And so what is the surface between? The surface is then a proof that if you do the first one and then you do the second one, then it's the same as the second one and the first one. If this is the second one and the first one together. So you can see how this sort of gives the picture of a torus, where if we glue it, we first get a cylinder, and then if we glue the cylinder, we get a torus. So that's why this makes sense. And then to sort of draw it, well, it's okay. Drawing it is somewhat difficult. The idea is that you're attaching a surface, and on one hand, you're attaching the surface by going along like this. That's going to sort of be half of the surface. And then on the other side, you're going to attach it by going along the other way. And that's going to create the surface of a torus, although I'm not doing a very good job of visualizing it. This is the way that I think about it. But we can show that it behaves like we would in a torus. And then the idea is that well, if I draw a torus in another way, this is how we usually draw it in math. And sort of, you can imagine that there's sort of a base point here. Then there's one circle going around the interior. And then there's another circle going around here. And if you sort of imagine it, you can take the circle and you can rotate it around. So T2 looks like the product of S1 times S1, where this is just the usual Cartesian product, so an odd-dependent sigma type. And this is going to be a characterization that we're going to prove, presumably next tutorial. Okay, so are there any other questions? Hopefully a bunch of the stuff was useful. Anyway, okay, I'm going to stop the recording.